Okay, so thank you for coming for our last lecture. Well, there's only one thing I would like to discuss in terms of our lectures today is how we create these electromagnetic waves. And after that, we can just review some of the questions if you have any about the physics, or just continue chatting, and as you wish. I will spend something like 1 hour. It will take me 1 hour to discuss how we generate these electromagnetic waves. Now, before we start, do you have any questions?
Gelmedim dersin.
Yes. Mutual inductance, okay. Inner solenoid. Well, let's see. This is the question we have. So here we have an inductor, which creates a magnetic field. This is a solenoid. Inside this solenoid, we put another solenoid. And the question was, what is the mutual inductance between these two? Right? Now, how do we define the inductance? Basically, if you calculate the flux going through one object, one solenoid, it should be equal to the mutual inductance, let's just denote it by M, multiplied by the current running on the other solenoid. This is how we define the mutual inductance. So let's see. What is the magnetic field created by the outer inductor? Mu0 I times small n, where n is the number of turns per length of the outer inductor, outer solenoid. Now, what is the flux that this magnetic field creates? Let's say this is R1. This is R2. The flux created in the inner solenoid is just B times pi R1 squared times N. This is R1 because we are calculating the flux that goes through the inner solenoid.
The example that you solved in class was different. It was that there was a current running through the inner solenoid and the outer solenoid was the...
Okay, let's do it again. Let's do that example. And let's prove that the mutual inductance is the same both ways. So we have this outer solenoid, and now we have the inner solenoid, which carries this current I. So there is a magnetic field in the inner solenoid. Well, let me just correct this one. There is a magnetic field in the inner solenoid whose magnitude is mu0 I times n. This time n, let's say n inner. Is the number of turns per unit length. Now here, B is 0. So what is the flux created on the outer solenoid? Flux is B dot ds. I can split it into two. B dot ds in the inner solenoid plus B dot ds in between the solenoids. But in between the solenoids, there is no magnetic field. So there's only the magnetic field inside the inner solenoid, and hence the flux created in the outer solenoid is nothing but the flux created in the inner solenoid, so it is equal to B times pi R1 squared times N out. So it is still R1, because out of the inner solenoid there is no magnetic field.
I was thinking of using the magnetic field inside and the area of the outlet, the whole thing.
But the
problem is that magnetic field might be uniform, right?
magnetic field is not uniform everywhere. So there is there is one region where the magnetic field lines are uniform. There is another region where the magnetic field lines are still uniform because there is zero magnetic field. It's uniform. Other questions? What do you mean by a conservative field? Let's look at that. Let's start with that one. So the loop integral, let's say the electric field, E dot dl, this should be equal to 0. If this is satisfied, E is conservative. This is the definition of a conservative field. Now the problem is we know the Faraday's law, which says that E dot dl is equal to minus d phi b by dt. So if d phi b by dt is non-zero, then E is non-conservative. Well, you can actually go both ways. If the electric field is non-conservative, then the flux should be changing. And for the magnetic field, you can use, well, the magnetic field is not conservative anyway. Other questions? Now let's go over what we had done yesterday. Now we had these two, okay, this is the x-axis, the y-axis, the z-axis, and we said that it is possible to have electric and magnetic fields such that the electric field at the point R at the time t is equal to E0 cosine kx kz minus omega t in the x direction, and the magnetic field has more or less the same form in the y direction. And then we said that, okay, this is possible only if E0 over B0 is equal to the speed of light, which we found out that it has to be equal to 1 over square root of epsilon 0 mu 0. If this is satisfied, then it is possible to have such a field. But if you just track how we made this proof, how we obtained this result, this conclusion over here that it is possible to have such a field. We had these electric fields, and we also had the magnetic fields perpendicular to it. So this is the magnetic field. But we only used in our proof this rectangle over here and this rectangle over here. We only used these two very small rectangles. We didn't really use any property of the electromagnetic field over here. And it can just have an arbitrary shape over here. The only thing is that it should have some time dependence at this point. So basically what that means is that the electric and magnetic field doesn't really need to have this shape. They can have arbitrary shapes. But nevertheless, it's most of the time important to study the cosine and sine functions because of what's called the Fourier theorem. So what is Taylor's theorem? You have already studied.
We can write the function in a combination of derivatives.
No, its derivatives at a given point, which are just numbers multiplied by polynomials. So Taylor's theorem basically states you that you can write any function, you can approximate any function as a polynomial. And in the limit that you take infinitely many terms, then that approximation is exact. That is Taylor's theorem. So if you have f of x, you can write this as some constants times x minus x0 raised to the power n, where these n's are the nth derivative of f evaluated at the point x0. And we also have this 1 over n factorial. This is Taylor's theorem. Right? This is familiar. It should be familiar. Now, this is Taylor's. Well, you will learn the details of the Fourier theorem, which basically states that if you have any function, you can write it as a sum of the sines or cosines. And I will not write the explicit expression, I will not go into it. Just know that if you have any function, you can just write it as a sum of the sines and cosines. You don't have to use these polynomials. So if that is the case, I mean, whatever the shape of our electromagnetic wave is, we can always write it in the form of sum of such terms. So whatever these functions have, whatever properties these have, their sum will also have the same property. So whatever the frequency is, they all travel at the speed of light. So if you just take their sum, whatever the shape of your electromagnetic wave is, it will always travel at the speed of light. So that is something I will use. Now the question we would like to discuss is how to create electromagnetic waves. So do you have any idea, any suggestion? You see, we already had shown that electromagnetic waves have energy, they have momentum, and hence they conserve momentum. And even if you have objects that have electromagnetic interactions, their linear momentum will still be conserved. So that kind of tells you how we can generate it.
Basically, we know that once electrons are they go to...
Well, we don't know quantum mechanics, we are just doing classical physics. So there's no question of excitation.
Or I can say when charges lose energy.
When? They don't need to lose energy. Their momentum should change though. You see, we had discussed this problem. We had said that, okay, so in this system, the momentum of the charges, the sum of the momentum of the charges is changing. But that doesn't mean that the momentum is not conserved. What happens is the change in the momentum of these point charges is transferred into the electromagnetic wave. So this system creates an electromagnetic wave. It should create an electromagnetic wave so that we can create energy, we can conserve any momentum. So what kind of motion these objects will do after this instant? Accelerated motion, right? So let's look at accelerated motion. That is what we will be doing. Now what I will assume is that the acceleration of my object, I will assume I have some charge. It is accelerated, let's say, in the x direction for a very small amount of time. So it is, let's say, a0 for time. At t equal to 0, it starts accelerating. It accelerates for a very small amount of time. Let's call it tau. And 0 otherwise. So out of this interval, it is just making motion with constant velocity. Now, what will the electric field lines look like? Now, and I will also assume that the maximum speed is much less than the speed of light. So it's just a slowly accelerating, slowly moving charge. It is accelerating, but nevertheless it's not reaching acceleration speeds. Now you can generalize this argument for objects moving at the speed of, close to the speed of light, but for our argument at least, this is enough. So this will be the motion of my object. So let's say this is the t equal to 0. This is the z coordinate of its motion. This is the time t is equal to tau. No, this is the velocity of my object, the z component. So it is 0. Then it is increasing linearly. And then after that, it will be just 0 again. Now, since it's moving slowly, we had already seen that the electric field lines of this object is just radially outward when it is moving at constant velocity. If it is moving at constant velocity, this is my object char, object q, this is v. This will be more or less how the electric field lines will look like if v is much less than the speed of light. I will also use this one. So let's see, my object starts over here, right at this point. Then it accelerates for a time tau. So from that point, it will reach, let's say, this point at the time. This is at time t equal to 0. This is at t is equal to tau. Then at a later time t, it is somewhere over here. And now I'm looking at it at the time t. Now we had seen that any change in the electric field propagates at the speed of light. So that is one thing I will use. So at the time t equal to 0, its electric field lines were just radially out. This is how they look like at the time t equal to 0. So if I just, let me just imagine such a sphere around it. And the radius of this sphere, let's call it r. And r is equal to c times t. Now, any change in the electric field didn't yet reach out of that sphere, because any changes in the electric field, any fluctuations, they just move at the speed of light. The changes due to this acceleration didn't yet reach out of the sphere. They're all confined inside. So out of the sphere, at the time t, the electric field lines are still uniformly outward. So this is what the electric field lines should look like out of the sphere of radius c times t. Because before the time t equal to 0, my object was at rest. So I know that the electric field lines are radially outward, uniformly radially outward. And at the time t, that changes in the electric field due to the motion of my object didn't yet reach these points. So they don't yet know that my charge has been accelerated. So they still stay radially outward. How? Now we will be discussing that one. There's also, now my charge is over, my object is over here. The electric, now after this point, it's just moving at constant velocity, at a small velocity, but a constant velocity. And we also said that if an object is moving at constant velocity, the electric field line should also be more or less the radial. That shouldn't change. But of course, it has been moving at constant velocity. We don't know what happens when it's accelerated, but we know what happens when it is moving at constant velocity. So it has been moving at constant velocity between the time t is equal to tau and t is equal to t. So we know that within this interval, within this time interval, the electric field lines are radially outward. So there's, let me imagine, such a sphere. This is R1. This radius is R2, and R2 is C times T minus tau. Now, within this sphere, the electric field lines will again be just radially outward, uniformly distributed, because my object is moving at constant velocity. So I know these two limits. And I will be also assuming that tau is very small. So if tau is very small, I can even neglect the tau over there. So this is kind of an exaggerated sketch. Now what happens in between? Oops, sorry. So these are the electric field lines inside this inner sphere. No, I'm not talking about the Doppler effect, nothing. There are no waves. I will not be, well, there are waves, but no Doppler effect. Also, the Doppler effect will be important only if you are traveling at speeds close to the speed of light. And since I'm assuming that the speed of the object, even after the acceleration, is very small, there's no such effect. Now, what happens in between? Well, we might not know, but we know that it happens for a very small amount of time. That's one thing we know. We also know, so that means since it has happened in a very small amount of time, the distances over here, which although I have exaggerated them, this shell is very thin, not so thick, because the change has happened at a very small amount of time. That is one thing we know. Second thing we know, electric field lines cannot break. They have to be continuous, because if they break, it means that, they can only break on charges. That is what Gauss' law tells me. And in this region, there are no charges. So they cannot break, they cannot end. So these electric field lines should connect to the outer electric field lines in a continuous manner. Well, the exact shape is not that important, but more or less they will look like this. This will connect here, this will connect here, this will be straight. This is how the electric field lines will look like. Again, the exact shape is not that important, because imagine this is very thin, this thickness is very thin, and if that thickness is very thin, well, any shape function will just look like a line, a straight line. So whatever the exact shape is in a very small region, it will just be just a straight line. So I will be just using the fact that it's a straight line. Any questions up to this point? So this is basically what the shape of the electric field lines should look like, approximately. And now what we will be doing is, what is the electric field in this region? That is what I would like to know. We already know the electric field over here. We know the electric field outside. We don't know what it looks like inside. Now, if you look at over here, there are two components to that electric field. One is radially outward, the other one is tangential. Let's look at their ratio. So at this point, this is the electric field. Electric field has these two components. This is the radial component, let's say this is the tangential component. Well, let me draw it a bit larger. So this is the electric field at that point, in that small shell. It will have a radial component and the tangential component. It is this one is the radial component. This is the tangential component. The electric field is equal to the radial part plus the tangential part. Just the vectorial sum. Now let's look at the ratio of those two. The tangential component divided by the radial component. Now this ratio will give me the tangent of this angle. I'm just taking the ratio of the magnitudes, the ratio of this side divided by this side. They are perpendicular to each other. That's just the tangent of this angle over there. But that angle over there is nothing but this angle over there do you agree? Now let's see, let me draw a few more angles. There I have a right triangle. I can just imagine moving this all the way to here. I have this other right triangle over here. Now this angle is theta, this angle is theta. Another color. Which color do you like? Yellow. No, you won't like it. Well, let me draw it again. So this is basically what we have. This is This is the position of my charge. So there is a electric field line that starts from my charge and moves in that direction. And it continues for a distance that is approximately c times t. Then here I have another radial line parallel to that one. And it crosses this point, this line here. And this distance, this is ct minus tau, and that distance is c times t. Do you agree? Okay, I need some volunteers. I need 2 volunteers. Now we are at time t, okay? Now here's the initial electric field that I created. So at time t equal to 0, he starts going on, and I start accelerating. He starts to go on. Then we reach the time tau. At the time tau, after the time tau, there is another electric field line that is moving. And then we keep going. Both of them keep going. They both move at the same speed. Stop, 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 stop. Now she had traveled the distance c times t minus tau, because that I sent her at the time tau. I sent him at the time t. So he traveled c times t. That is this point over here. He is at this point. She is at this point. Since I sent her tau seconds later, the difference in the distances they traveled is c times tau. Now the question is this one. Okay, thank you. In between, what happens? How can I determine this angle over there? Let me also call this angle over here phi. Let me just give it a different name. Now, what is this length? Now, this length over here, let's just call it d. That is the total distance that I covered in the time t. D is approximately v times t. Of course, there is some acceleration, but the distance I covered during that acceleration is very small. So most of the time, I'm just carrying out motion with constant velocity. My speed is v, so this is the total distance that I covered. No? Let's go back. I'm looking at my system at this time t. The total distance covered is all of this area. Well, I'm just ignoring this area over here and writing the total area to be approximately v, that is the maximum speed over here, v times t. I'm kind of overestimating the distance I covered, but the error I introduce is negligible. It will be proportional to tau, which is small.
Can you show the shape? Motion is continuous and some real function, but this doesn't seem like it.
Well, of course, these points over here, they are not really sharp angles. They are just curved angles. They're smooth. But I mean, they're smooth. But what I'm assuming is, at a given instant, I start accelerating sufficiently fast. And then after some time tau, I just stop accelerating again sufficiently fast. So these are not angles. They are not pointed. They are smoothed out. But approximately, this whole thing looks like a sharp-cornered triangle. Approximately. And the errors will be small. Now, what is this distance over here? d times sine phi. No, cosine phi. It's just here I have a right triangle. Here I have a right triangle. So this is d times cosine phi. This distance is d times sine phi. Now, similarly, this distance is also d times sine phi. And this distance over here is nothing but ct minus c times t minus tau minus d times cosine phi. This is the whole length. D times cosine phi is this length. C times t minus tau is this length. So what remains is this distance over there. Now I can write tangent theta. Tangent theta is equal to d times sine phi divided by, well, here if you look, this ct and this, they just cancel. C times tau plus d times cosine phi. Now minus. Do you agree? Well, the electric field is parallel to this one. the tangential component is along this line, and the radial component is along that line. ET over ER is nothing but just ET over ER. ET is this length, ER is this length, that is nothing but our tangent theta. The transversal component of the electric field divided by the radial component of the electric field is equal to tangent of this angle over there. So we kind of already have the tangential component of the electric field. In terms of the radial component, this should be ER times d sine phi divided by c tau minus d cosine phi. Now the radial component of the electric field, well, it doesn't really change much. I mean, the expression for the radial component at this point and the radial component at that point, the expressions are more or less the same. In between, it will be changing a bit, the radial component, but it will be probably the radial component of the electric field, its magnitude will be somewhere between the magnitude of the radial component at this point and let's say at that point. It will be somewhere in between those two. But the radial component of the electric field at this point and at that point, they are more or less equal, because we already assume that this region is very thin. Tau is very small. So that basically tells me that this is equal to 1 over 4 pi epsilon 0 q over r squared d times sine phi divided by c tau minus d cosine phi. Well, what we are doing is, now we know the radial component. So that's basically what we are assuming. But if we have an accelerated charge, if the charge is accelerating, we develop a tangential component. So you see, here there is a tangential component in this region. Now what we are trying to calculate is, what is the tangential component? It doesn't satisfy the Coulomb's law. You see, the tangential component, I mean, that is basically what formed these circular electric field lines, these induced electric field lines. So we are trying to calculate that one. And what we will be trying to show is that this tangential component, you see the radial component, it goes as 1 over r squared. What we want to prove is that the tangential component goes as 1 over r. Now, if we can prove that, what will we gain? Well, there will be a corresponding magnetic field, which will also be 1 over r. Do you agree? But this means the Poynting vector will be proportional to 1 over r squared. Remember, the Poynting vector was E cross B. E is 1 over r, B is 1 over r. So S is 1 over r squared. Here is our accelerated charge. Here is a surface at a very far away distance. S dot dA over this surface in the limit as r goes to infinity. You see, in that limit, S goes to 0, but dA also goes to the infinity. This goes as 1 over r, the surface area 1 over r squared, the area goes as r squared, so this will be a constant. So what does this mean? This basically means that even if you assume remember what pointing vector was. It was the energy flow. There is some energy going away from my charges even at infinity. Of course, it will be spread out very large, it will be very small in magnitude if you go sufficiently far away, but nevertheless, the energy going out of this huge sphere will be non-zero. That is basically you are sending some energy from here to somewhere else. It's now independent of you, it just can go up until infinity. That is what we call the electromagnetic energy. Or that is how the radios work. They are sending energy from their initial source to where we are. We are almost at infinite distances. So that is what we are trying to show. What we need to show is that the translational electric field is proportional to 1 over r. Furthermore, it is proportional to the acceleration of the object. If acceleration goes to 0, there is no radiation. Only if there is an acceleration, there is this is called the radiation field. This 1 over r dependence is a characteristic feature of the radiation field because only if it goes as 1 over r. You see, this radial part, 1 over r squared part, if there is a corresponding magnetic field, since it's moving, the magnetic field will be also 1 over r squared. So the pointing vector for this radial part will be 1 over r to the 4, the fourth power of the distance. And if you put that over here, it just goes to 0. So it's just telling me that I have this charge. If it is moving with some velocity, around this charge there is some energy stored. But that energy is significant only in the near vicinity of that charge. If you go away from the charge, there is no energy left. But if there is acceleration, then I have this 1 over r fields. And these 1 over r fields, they just go until infinity. Or let's say very far away distances. So that is what we are trying to prove. Yes? Well, you see, what creates this magnetic field? Changing electric field. Well, the magnitude of the electric field goes as 1 over r. So it's the rate that the electric field change also goes as 1 over r. So the magnetic field that it can create also goes as 1 over r.
So, sorry, the electric field normally when it's 1 over r squared. Why is it?
The radial part goes as 1 over r squared.
Why is the tangential part 1 over r?
That is what we are trying to prove, which we couldn't yet. Now, so we are over here. Well, it is still 1 over r squared. D is, what is D? D is V times T. Well, the speed of light is huge. So even if tau is small, c times tau would be large, much larger than this d. What is v over tau? You see, we had our object at rest, then it accelerates for a time tau, and after that time tau, its speed is v, So V over tau is the acceleration. Now, what is t? Now, y? T is R over C. Because this distance R, I'm looking at a point which is in this shell. But this shell, or R is equal to C times T. We had already written it over here. R is somewhere between R1 and R2. And R1 and R2, they are both approximately C times T. So that is why R is equal to C times T, approximately, or T is equal to R over C. So ET, this is 1 over 4 pi epsilon 0, Q times A sine phi over C squared. You see this tangential component of the, there's also 1 over R. So the tangential component is proportional to the acceleration. If there is no acceleration, there is no tangential component. If there is acceleration, there is a tangential component which is proportional to 1 over R instead of 1 over R squared. So this is what we call the radiation field. This electric field can just go to until infinity or very far distances. Now I will be taking one jump now. Now the electric field at the point R at the time t will be equal to 1 over 4 pi epsilon 0 c squared 1 over r q times sine phi times the acceleration, but the acceleration at the time t minus r over c. Not at the time t. You see, if you consider our object just accelerated for a very small amount of time and then stopped. And we are measuring the electric field at the time t, but this is proportional to the acceleration of the object at the time t equal to 0. So that is why we have if the acceleration is not just this simple function, but our object can be doing an arbitrary acceleration, not necessarily linear, nevertheless, not necessarily constant within that range, nevertheless the electric field, the tangential component, will have this form at the point r at the time t. Let us just make one more assumption. You see, we had already studied RLC circuits, right? Well, you see, this A over here, this tangential electric field is the electric field I measure at a distance r at the time t, right? But this acceleration over there is not the acceleration of the object at the time t. At the time t, the acceleration of the object is 0. It's not accelerating. It just accelerated for a very short amount of time, close to t equal to 0. So the electric field at a given time depends on the acceleration of my charge at an earlier time. How much earlier? Well, r over c earlier. At my point, you see, if I have an acceleration only at time t equal to 0, okay? So the acceleration is non-zero only if t minus rc, r over c, is, let's say, approximately 0. So only if this condition is satisfied, then the acceleration, this is equal to a constant, and which is non-zero, and the tangential electric field is non-zero. Now this is true for any point for any time. If you choose a point, let's say here, at this point, the tangential electric field is zero, right? But if you choose some point over here, that means this T minus R over C, now R is small, T minus R over C is a large number, and since it's a large number, my acceleration is zero. Since it is zero, the tangential electric field is zero, as it should be.
If T minus R over C is large number, why equals A 0?
Because the A of T, this is equal to A if T is between 0 and tau, and 0 otherwise. So that expression over there, I mean, up to this point, up to the previous line, up to this point, we were only looking at a point in this shell where there's some radiation. This is the generalization of the same expression. But this time, R and T can be arbitrary points. And this expression is equal to this one in my shell, and it is zero out of my shell. And that's basically what the tangential electric field is. My tangential electric field is equal to this one in the shell, and it is zero outside. So this is just a generalized expression. In the shell, yes. So you were saying that in the shell, T was equal to R over C. True. Because this is non-zero only if T minus R over C is approximately zero, but that is inside the shell. Now let me do one more step. What if the acceleration of the object is more complicated? Again, we had studied RLC circuits where we have the alternating current. Now what happens in the alternating current is that the current just changes its shape. The AC is equal to, let's say, I0 cosine omega t. So the current at one instant is moving in one direction, at the next instant is moving in the other direction. So if you consider any one charge, it is just moving back and forth. Just one charge in this current. So the acceleration of the charge, of a single charge, this will be equal to, let's say, A0 cosine omega t. So this single charge will create an electric field, the radiation electric field, which will be equal to 1 over 4 pi epsilon 0 c squared 1 over r q times sine phi times A0 cosine omega t minus r over c. Cosine omega t minus k, let's say r, where k is omega over c. But this is the plane wave that we had studied, except on this 1 over r dependence. This phi. Just give me one more moment, we will discuss what phi is. We will write it in a different form. Now let's just imagine we have a transmitter, which is basically an RLC circuit, probably, or an AC current, any AC current. So there are these charges that are oscillating, and hence accelerating. They are doing accelerated motion. And so they will be radiating some energy in terms of the electromagnetic waves, and this will be their shape. Let's say the transmitter is 2 kilometers from here. So what is the size of this room? More or less. 20 meters. Okay. So that end is like 2 kilometers from the transmitter. That end is 2 kilometers plus 20 meters. Well, that is more or less constant. It doesn't change. R is constant. So we have, in this room, the radiation field will be some constant, which will depend on all these parameters, our distance from the transmitter, this angle we will come, the charge is accelerating, these coefficients over here times this cosine. And that was the radiation field that we were discussing yesterday. Now let me just discuss what this sine phi is, and then I will let you go for a break. So this is what we were studying. We have this charge. It had an acceleration in this direction. And after that, it was moving in that direction. And we are looking for the electric field over here. This is the angle phi. And this is the direction of the ET. This is equal to 1 over 4 pi epsilon 0 c squared a at t minus r over c times q times, now let me put the q here, and then we have the 1 over r. Let me write it r squared, and here r, and then we have the sine phi. Look at this combination. The magnitude of one vector, it is this vector, multiplied with the magnitude of some other vector, multiplied by the sine of the angle between the two. Acceleration is horizontal, and phi is nothing but the angle between the acceleration and the radius vector, the position vector. So this is equal to q over 4 pi epsilon 0 c squared 1 over r squared, the magnitude of a cross r. What is the direction of a cross r? Out of the screen, right? This is a cross r. What is r hat cross a cross r? R hat is in that direction. This is the direction of R hat. A cross R is towards you. Right? R hat cross, this one is in this direction. Right? So this is R hat cross A cross R. Do you agree? So let's see. This electric field, the tangential component or the radiation field, is equal to q over 4 pi epsilon 0 c squared 1 over r a cross r hat cross r hat. Okay, this is just the vectorial form of the same expression. Whatever the acceleration is, whatever the acceleration of your object, of course, just keep in mind that this is the acceleration at an earlier time. This is the general form of the radiation field. So this is how you can create electromagnetic waves. Just accelerate the object. it is in the minus R cross A cross R. So plus A cross R cross R.
K is equal to K over C.
Here. Well, for an electromagnetic radiation, it had to be that way. That is what we had derived yesterday. But you see over here, if you just multiply it, the coefficient of R is omega over C. So I define this K to be omega over C. This is my definition. In this expression, there is no K. But in that expression, there is omega over C, which I define as K. And we already know from yesterday that the coefficient of distance and the coefficient of the time, if you take their ratio, it has to be equal to the speed. Okay, let's go for a break. After the break, if you show up, we can continue.